Right now, at a distance so vast that the number itself collapses language, an exact physical duplicate of you is breathing, thinking, and perhaps listening to a voice much like this one. It is not a metaphor. It is not a thought experiment. It is a consequence of the physics we currently trust. Your duplicate is not a clone grown in some distant laboratory. It is you, molecule for molecule, memory for memory, sitting in a room indistinguishable from yours, on a planet indistinguishable from Earth, in a galaxy indistinguishable from the Milky Way. You will never meet. You cannot communicate. The space between you is expanding faster than any signal could ever cross it. But if the universe is as large as the evidence suggests, the arithmetic leaves very little room for doubt. That other you exists, right now, beyond the edge of everything we can see. And the number that describes how far away is one of the strangest quantities anyone has ever had cause to write down. Hello, and welcome to Sidereal. Tonight we are going to spend some time at the edge of the observable universe, and then past it. If you find this kind of slow exploration useful for sleep or for winding down, a like or a subscribe genuinely helps the channel reach other people who are awake at this hour. And I am curious where you are listening from tonight. Drop your location and the time in the comments. That is the only housekeeping. Here is the question we are following. The universe we can see has an edge, but that edge is not a wall. It is not made of anything. It is a limit on how far light has been able to travel since the beginning of time, and it moves outward as the universe ages. So what is on the other side of it? By the end of tonight you will have 5 answers, each one built by working physicists, each one stranger than the one before, and each one arriving at roughly the same conclusion from a completely different direction. We are going to start with the edge itself, where it is, how it was found, and why it turns out to be not one boundary but 2. Let's begin. When you look at the night sky from a genuinely dark place, far from any town, the stars feel like a promise that goes on forever. They do not. What you are seeing is roughly 9,000 stars, and only about half of those are above the horizon at any moment. Every one of them belongs to our own galaxy. Almost all of them are within a few thousand light years. Beyond them, 3 or 4 faint smudges resolve, on a good night, into other galaxies. That is the unaided human inventory of the universe. It is a very small catalogue. With a telescope you can go much further, but even the most powerful instruments ever built eventually arrive at a limit, and the limit is not a question of engineering. It is not that the light is too faint, or that the mirror is too small, or that the atmosphere is in the way. Beyond a certain distance there is simply no light to collect, because no light has had time to arrive. The wall at the end of the observable universe is not made of matter, it is made of time. The observable universe is a sphere, and you are at the centre of it. So is every other observer, everywhere, which is the first hint that the sphere is a fact about us rather than a fact about the cosmos. Its radius is about 46.5 billion light-years. That number surprises people who have already learned that the universe is 13.8 billion years old, because it seems to say that light has travelled 3 times further than it had time to travel. It has not. The light took 13.8 billion years, but the space it was crossing kept stretching while it was in transit, so the point of origin is now much further away than the distance the photon actually covered. The photon ran a marathon on a track that was being pulled longer beneath it. The oldest light we can detect left its source about 380,000 years after the beginning. Before that moment, the universe was too hot for atoms to hold together. Electrons moved freely among bare protons and helium nuclei, and free electrons are extraordinarily good at scattering light. A photon in that environment could not travel any meaningful distance before being knocked in a new direction. The universe was opaque, in the way that the inside of a cloud is opaque, and for the same reason. Then the expansion cooled it to about 3000 Kelvin, and the electrons were captured into orbit around the nuclei. Neutral hydrogen formed. The fog cleared in what was, on a cosmic timescale, an instant. The photons that were released at that moment have been travelling ever since. They have been stretched by the expansion of space by a factor of about 1100, which has dragged them out of visible light, through infrared, and into the microwave band. They arrive now as a faint glow that comes from every direction in the sky, with a temperature of 2.725 Kelvin. That is the cosmic microwave background. It is the most distant light that exists in any electromagnetic band, and it marks the inner surface of everything we can see. It was found by accident by two men who spent the better part of a year trying to get rid of it. In 1964, Arno Penzias and Robert Wilson were working at Bell Telephone Laboratories in Holmdel, New Jersey, with a large horn-shaped antenna that had been built for early satellite communication experiments. They wanted to use it for radio astronomy, and radio astronomy requires knowing exactly how much noise your instrument produces on its own. So they pointed it at what should have been empty sky and measured the background hiss at a frequency of 4080 MHz. There was more hiss than there should have been. It corresponded to an excess temperature of about 3.5 Kelvin, and it would not go away. They checked everything. They tested the electronics. They looked for interference from New York City. They considered the possibility that the signal came from the remains of a nuclear weapons test conducted in the upper atmosphere 2 years earlier. They found a pair of pigeons nesting in the throat of the antenna, which had coated the interior with what Penzias later described, in the driest possible language, as a white dielectric material. They evicted the pigeons, cleaned the horn, and taped over the joints. The pigeons came back. They were removed again by less gentle methods. The hiss remained, identical in every direction, unchanging as the Earth turned and the seasons passed. 30 miles away, at Princeton, a group led by Robert Dicke had spent months building a small antenna specifically to look for exactly this radiation. They had reasoned that a hot early universe should have left a cooled remnant glow, and they were preparing to hunt for it. Penzias heard about their work through a chain of casual conversations and telephoned Dicke. And Dicke listened for a while, hung up, turned to his colleagues, and said that they had been scooped. The two groups published side by side in the same journal in 1965. Penzias and Wilson described a measurement and offered no interpretation. Dickey's group explained what the measurement meant. Penzias and Wilson received the Nobel Prize in 1978. Dicke did not. The boundary defined by that radiation is called the particle horizon. It is the maximum distance from which any signal, of any kind, could have reached us since the universe began. It is not fixed. It grows by 1 light second every second, as the universe ages and light from further away completes its journey. Every second, a thin new shell of the cosmos becomes visible to us for the first time. In principle, given enough patience, we would eventually see everything. We will not. There is a second horizon, and it works in the opposite direction, and it was not properly understood until the very end of the 20th century. To see where it comes from, we need to go back to the moment when anyone first realized the universe was expanding at all, and that story begins with a woman whose name is missing from most accounts of it. Henrietta Swan Leavitt was employed at the Harvard College Observatory as one of a group of women hired to measure and catalogue stars on photographic plates. They were called computers because computing was what they did, and they were paid about 25 cents an hour. Leavitt was assigned the variable stars of the Magellanic Clouds. Over several years, she identified 1,777 of them. In 1912, she published a short paper concerning 25 of those stars, a type known as Cepheid variables, which brighten and dim on a strict repeating cycle. What she found was a relationship so simple it could be plotted on a single graph. The longer a Cepheid takes to complete its cycle, the more luminous it actually is. And because all of the stars she studied were in the same cloud, at roughly the same distance, their apparent brightnesses could be compared directly, which meant the relationship was real and not an artifact of distance. Measure the period of a Cepheid anywhere in the sky, and you know its true brightness. Compare that to how bright it looks from here, and you know how far away it is. Leavitt had built the first reliable measuring rod that could reach beyond our own galaxy. She died of cancer in 1921, at the age of 53. A Swedish mathematician tried to nominate her for the Nobel Prize 4 years later, and discovered she was no longer alive to receive it. Everything that follows in this section was measured with her ruler. In the 1920s, a Belgian priest and physicist named Georges Lemaitre worked through the equations of general relativity and found a solution that Einstein had not wanted to find. The equations described a universe that could not stand still. It had to be either expanding or collapsing. Lemaitre published in 1927 in a Belgian journal that almost nobody outside Belgium read, and he included a prediction: distant galaxies should be receding from us at speeds proportional to their distance. He even estimated the constant of proportionality. Einstein met him at a conference that year and told him that his mathematics was correct but his physics was abominable. 2 years later, at the Mount Wilson Observatory in California, Edwin Hubble used the 100-inch Hooker telescope to measure distances to spiral nebulae using Leavitt's Cepheids and combined them with redshift measurements that had been painstakingly gathered over the previous decade, mostly by Vesto Slipher at the Lowell Observatory. The galaxies were receding. The further away they were, the faster they were going. The relationship was linear, exactly as Lemaitre had predicted. Einstein had inserted a term into his field equations in 1917 for the express purpose of holding the universe still, a repulsive pressure exactly balancing gravity. He abandoned it after Hubble's result and reportedly called it his greatest blunder. That phrase comes to us second-hand through the physicist George Gamow, and there is reasonable doubt about whether Einstein ever said it in those words. What is certain is that he removed the term. It is also certain that 70 years later it came back, and that it turned out to be the most important number in cosmology. The rate of that expansion is called the Hubble constant. Its value is somewhere around 70 kilometers per second per megaparsec, which means that for every 3.26 million light-years of distance, the recession speed increases by about 70 kilometers per second. And here we run into one of the genuinely unresolved problems in modern astronomy, which is that we have two excellent methods of measuring this number and they do not agree. Measure the expansion rate directly, using Cepheids and supernovae in relatively nearby galaxies, and you get something close to 73. Infer it instead from the detailed structure of the cosmic microwave background, running the physics of the early universe forward, and you get 67.4. The error bars on both measurements have been shrinking for 20 years, and instead of converging, the two numbers have separated. The discrepancy is now statistically severe enough that it is unlikely to be a mistake in either measurement. It has a name in the literature. It is called the Hubble tension, and nobody has explained it. And quote, "It is one of the clearest signs we currently have that the standard model of cosmology is missing something." Now to the second horizon. If the expansion of space carries galaxies away from us at speeds proportional to their distance, then there is a distance at which that speed reaches the speed of light. This is not a violation of relativity. Nothing is moving through space faster than light. The space itself is stretching, and there is no rule against that. The boundary where the recession speed equals light speed is called the Hubble sphere, and it currently sits at about 14.4 billion light-years. For most of the 20th century, this was thought to be a fairly harmless piece of geometry, because in a decelerating universe the Hubble sphere expands faster than the galaxies within it, and light emitted from beyond it can eventually cross back in and reach us. Objects that seemed permanently unreachable would gradually swim into view. Then, in 1998, two competing teams of astronomers measured the expansion history of the universe using exploding stars and found that the expansion is not slowing down. It is accelerating. We will come back to that discovery in detail later tonight, because it deserves its own hour. For now, only the consequence matters. In an accelerating universe, there is a distance beyond which light emitted right now will never reach us, no matter how long we wait. Not in 100 billion years. Not ever. The space in between is being added faster than the light can cross it, and the deficit grows without limit. That boundary is called the cosmological event horizon, and its radius is roughly 16 billion light-years. Lie still for a moment and consider what is arriving. The light landing on the roof above you left its source before there was a source to leave. That is not a figure of speech. The photons of the cosmic microwave background were released 380,000 years after the beginning, when there were no stars, no galaxies, no elements heavier than lithium, and nothing anywhere that could be described as an object. They have been in transit ever since, without interruption, without absorption, crossing 46 billion light-years of expanding space, and they are landing on the roof now, and on the road outside, and on you, at a rate of something like 400 million per second through every square meter. You cannot feel them, They carry almost no energy, which is why they pass through the building and through your body without effect. But they are the reason we know any of this. Every measurement in this script traces back to that light. The flatness of space, the age of the universe, the proportions of matter and dark energy, all of it was read off the pattern in that glow. It is still arriving. It has never stopped arriving, and the surface it came from is the closest thing the universe has to an edge. Sit with the difference between the two horizons, because it is the hinge of everything that follows. The particle horizon, at 46.5 billion light-years, is the limit of what we can see. The event horizon, at 16 billion light-years, is the limit of what we can ever touch, influence, or receive a message from. Almost every galaxy we can currently see lies outside the second boundary. We can watch them. We can photograph them. We can measure the chemistry of their stars. And there is nothing any of us could ever do at any point in the future of the universe that would have the slightest effect on them, or they on us. The situation gets worse. As the acceleration continues, more and more of the visible universe crosses that line. The galaxies do not vanish suddenly. Their light dims and reddens as it is stretched further and further. The images freeze and fade, and eventually the last photons that were emitted before the crossing arrive, and there are no more behind them. In about 100 billion years, an observer in the Milky Way will see nothing outside the local group, the small collection of galaxies bound tightly enough by gravity to resist the expansion. Everything else will have gone dark. Two physicists, Lawrence Krauss and Robert Scherer, worked through the implications of this in a paper in 2007, and their conclusion is unsettling in a very specific and unusual way. An astronomer in that far future, doing careful and honest science with excellent instruments, would observe a single island galaxy in a static, empty void, no red-shifted galaxies, no cosmic microwave background, which by then will have been stretched to wavelengths longer than the horizon itself and become undetectable. No evidence of expansion, no evidence of a Big Bang, no evidence that anything else ever existed. They would conclude, correctly according to all available data, that they lived in an eternal and unchanging universe consisting of one galaxy surrounded by nothing. They would be wrong. They would have no way of knowing they were wrong. Which raises a question about our own position that is not comfortable and does not have a clean answer. We are doing cosmology in a window. The evidence that lets us reconstruct the history of the universe is available to us because we happen to be observing in the era when it is still visible. There is no principle guaranteeing that this window is wide, or that we are near its beginning, or that everything important is still inside it. So the horizon is not a wall, it is a limit on light, and it is a limit on causality, and neither of them is a limit on existence. The universe does not stop at 46.5 billion light-years. It almost certainly continues, and the only serious question is how far. That question turns out to depend on the shape of space itself, and on a measurement made from a balloon floating above Antarctica. There are only three possibilities for the overall geometry of the universe, and which one is correct determines whether it is finite or infinite. This is not a philosophical distinction. It is a measurable property, and it has been measured. General relativity says that the presence of mass and energy curves the geometry of space-time. On a small scale, this produces the effects we recognize as gravity. On the larger scale, taking the average density of everything in the universe, it produces an overall curvature of space itself. There is a critical density, a specific quantity of mass and energy per unit volume, at which the curvature comes out to exactly zero. Above it, space curves positively, closing back on itself. Below it, space curves negatively, opening outward without limit. The two-dimensional analogies are worn, but they work. So here is one. Once. Draw a triangle on a flat sheet of paper, and the interior angles sum to 180 degrees. Draw the same triangle on the surface of a sphere, and the angles sum to more than 180, because the surface bulges outward beneath the lines. Draw it on a saddle-shaped surface and the angles sum to less. In each case, the geometry can be discovered from inside the surface, by measurement, without ever stepping outside to look. That is the crucial point. We cannot get outside the universe to inspect its shape. We do not need to. A positively curved universe is finite. Travel far enough in a straight line, and you return to where you started, having never turned. It has a definite total volume, a definite total number of particles, and no edge, which is a combination that takes a while to accept. A flat universe or a negatively curved universe, provided its topology is simple, is infinite. Not extremely large, infinite, endless, in every direction, with no total volume and no total particle count. So the entire question of whether there is a copy of you somewhere reduces in the first instance to a measurement of angles. The problem is finding a triangle. To detect curvature over cosmological distances, you need an object of known physical size at a known enormous distance, and then you compare its true size to its apparent size. If the universe is flat, the apparent size follows straightforward Euclidean geometry. If space is positively curved, it acts as a lens, and the object appears larger than it should. Negative curvature makes it appear smaller. For most of the 20th century, no such object was known. It turned out to be hiding in the cosmic microwave background. Before the universe became transparent, in that hot fog of charged particles, there was a competition between two forces. Gravity pulled matter into the slightly denser regions. Radiation pressure pushed back out. The result was oscillation. The primordial plasma rang like a struck bell, with pressure waves propagating outward from every overdense region at a speed of about half the speed of light. When recombination happened and the photons were released, those waves froze in place. Their imprint is still there in the cosmic microwave background as a pattern of very slightly hotter and cooler patches, varying by about 1 part in 100,000. The variation was first detected by the Cosmic Background Explorer satellite in 1992, a result that the astrophysicist George Smoot described at the press conference in terms he later regretted. It won him a Nobel Prize in 2006, alongside John Mather, whose measurement of the background spectrum matched the theoretical prediction for a perfect thermal glow so precisely that when he presented it, the audience of astronomers applauded a graph. Here is why those patches are the triangle we needed. The largest wave that could have completed a single oscillation before the photons were released has a known physical size, calculable from the fundamental physics of the early plasma. It is about 150 megaparsecs, roughly 480 million light-years in the geometry of today. It is a standard ruler laid down across the sky at a distance of 46 billion light-years, with its length known in advance from theory rather than measured from observation. Measure the angular size of that pattern on the sky, compare it to the size it should have, and you have measured the curvature of the universe. The first measurement good enough to do this came from an instrument called Boomerang, a telescope suspended beneath a helium balloon the size of a football stadium, flying at an altitude of about 37 kilometers above the Antarctic ice. The altitude matters because water vapor in the atmosphere absorbs microwaves, and at that height there is almost none left above you. The Antarctic location matters because a circumpolar wind pattern in the southern summer carries a balloon in a large circle and returns it approximately to its starting point, which means the instrument can be recovered. It launched from McMurdo Station in late December of 1998 and flew for 10.5 days. When the data were analysed, the pattern of hot and cold patches in the cosmic microwave background had an angular scale of just under 1 degree, which is what a flat universe predicts and what neither a positively nor a negatively curved universe predicts. The team, led by Andrew Lang and Paolo De Bernardis, published in the spring of 2000, "Space is flat" to within the precision of the measurement. That precision has improved enormously since. The Wilkinson Microwave Anisotropy Probe, launched in 2001, refined it. The Planck satellite, launched by the European Space Agency in 2009 and operating until 2013, refined it further. The current figure from the final Planck data release is that the curvature of the universe is 0 to within about 0.4%. If space is curved at all, it is curved so gently that the radius of that curvature is at minimum several hundred times larger than the entire observable universe. Flat, then, which appears to settle the question and does not. Flatness gives you infinity only if the topology is simple, and topology is a separate property from curvature. Take a flat sheet of paper, which is unambiguously flat, and roll it into a cylinder without stretching it. The geometry is unchanged. Every triangle drawn on it still has angles summing to 180 degrees. But now, if you walk in one direction, you come back to where you started. The surface is flat and finite at the same time. Do the same in 3 dimensions and you get a flat but finite universe, sometimes described as a 3 torus, where travelling far enough in any direction returns you to your origin. If that were the case, the universe would repeat, but not in the way we are building toward tonight. It would repeat because it is the same region seen again from a different angle, like standing between 2 mirrors. The copies would not be independent. They would be reflections. There is a way to test for this, and it is beautifully direct. If the universe wraps around on a scale smaller than the observable universe, then the sphere of the cosmic microwave background intersects itself. The same physical region of the early universe would be visible in 2 different directions in the sky, and it would produce 2 identical circles of temperature fluctuations, matched pattern for pattern, in 2 separate parts of the map. Neil Cornish, David Spergel and Glenn Starkman proposed this test in the late 1990s, and it is known as the search for matched circles. It has been carried out, repeatedly, on the highest quality data available. No matched circles have been found. The conclusion is a lower limit rather than a proof. If the universe does wrap around, it does so on a scale larger than the observable universe, which is to say that any repetition from topology is outside our view entirely. There was one serious specific proposal worth mentioning because it shows how the argument runs when it is done carefully. In 2003, the French cosmologist Jean-Pierre Luminet and his collaborators published a paper in Nature suggesting that a particular finite geometry called Poincare dodecahedral space could explain something odd in the data. The largest scale fluctuations in the cosmic microwave background are weaker than the standard model predicts. In a finite universe, waves larger than the universe itself cannot exist, so the largest scales would be suppressed exactly as observed. The geometry Luminet proposed tiled space with 12-sided cells, and it predicted a specific set of matched circles at a specific angular size. The circles were looked for. They were not found. The proposal is not formally excluded, but it is not supported either, and the suppression of large-scale power remains unexplained. One more small item on the list of things the standard model does not quite account for. So where the evidence actually leaves us is this. Space is flat to the limit of our ability to measure. There is no sign of it wrapping around on any scale we can probe. Nothing in the data requires the universe to be finite, and the simplest reading of the data, the one that adds no additional assumptions, is that it is not. The inflationary picture pushes hard in the same direction. If a microscopic patch of space expanded by a factor of at least 10 to the power of 26 in a fraction of a second, then any curvature it originally had was flattened out of existence in the way that the surface of a balloon becomes locally flatter the more you inflate it. Inflation does not merely permit a flat universe. Inflation, it predicts one, and it typically predicts a total universe vastly larger than the region we can see. In many versions of the theory, the true extent is not merely large, but genuinely without end. None of this is proof. It is worth being precise about what we have and what we do not. We have a measurement of flatness with a stated uncertainty. We have a theoretical framework that predicts flatness and predicts enormous size. We have a failed search for the signature of a finite topology. We do not have, and cannot have, a direct observation of anything beyond the horizon. The infinite universe is the simplest model consistent with everything we can see. It is not the only one, but if it is true, something follows immediately, and it does not depend on any further assumption. It depends only on counting. In an infinite space filled with matter at roughly uniform density, there are infinitely many regions the size of our observable universe, and there are only so many ways to arrange the contents of a region that size. A finite number of possible arrangements, an infinite number of regions. The consequence is not a matter of opinion. Someone worked out exactly what it is, and exactly how far away the nearest instance would be. The argument is easiest to see in a form that has nothing to do with cosmology. Take an ordinary deck of playing cards and shuffle it. The number of possible orderings is about 8, followed by 67 zeros. That is an enormous number, far larger than the number of seconds that have elapsed since the beginning of the universe, and it is why any well-shuffled deck is almost certainly in an arrangement that has never occurred before in human history and never will again. Now suppose you could shuffle an infinite number of times. Every possible ordering would appear. Not most of them, all of them. Thanks for watching, and each one would appear not once but infinitely often, because after any finite number of shuffles you still have infinitely many remaining. The size of the set of possibilities is irrelevant. Any finite set, sampled infinitely often, exhausts itself and then repeats without end. The physical universe, if it is infinite, provides the infinite shuffles. Space itself is the sequence of draws. Each region the size of our observable universe is one deal from the deck. Everything now turns on whether the number of possible arrangements is finite. If a region of space could be configured in infinitely many distinguishable ways, the argument collapses. And classically, it could. In classical physics, a particle can sit at any of a continuum of positions, and there is no smallest meaningful difference, so the number of configurations of even a single particle is already infinite. Quantum mechanics closes that door. States that differ by less than a certain amount are not merely hard to distinguish. They are not different states. Combine this with a limit on how much information a region of space can hold, and the number of possible configurations of any finite volume becomes finite. Very large, but finite. That limit came from an unexpected direction, and from a graduate student who was told by nearly everyone that he was wrong. In the early 1970s, Jacob Bekenstein was working on his doctorate at Princeton, under John Archibald Wheeler. Wheeler had a habit of posing questions that sounded like idle conversation and were not. He asked Bekenstein what happens when you pour a cup of hot tea into a cup of cold tea. The mixture reaches a uniform temperature, and the entropy of the universe increases, and that increase is irreversible. You cannot unmix it. Now, Wheeler said. Suppose you drop the two cups into a black hole instead. The entropy is gone. The black hole is described by only three numbers: its mass, its charge, and its angular momentum, and it retains no memory of what fell in. So the total entropy of the universe has decreased, and the second law of thermodynamics has been violated, and you have committed the crime and destroyed the evidence. Bekenstein's answer was that the entropy is not gone, it is in the black hole, and he proposed that the entropy of a black hole is proportional to the area of its event horizon, not its volume. That proportionality is the part that matters, and the part that nobody expected. Entropy measures the number of microscopic arrangements consistent with a given macroscopic state, which is to say it measures information. Every intuition says that the amount of information you can store in a region should scale with its volume, because you can fill the interior. Bekenstein's result said it scales with the surface area of the boundary. Stephen Hawking initially thought this was wrong, for a specific and reasonable reason. Anything with entropy has a temperature, and anything with a temperature radiates, and a black hole was by definition something from which nothing could escape. In 1974, working through the behavior of quantum fields near an event horizon, Hawking discovered that black holes do radiate. He had set out to disprove Bekenstein, and had instead confirmed him, and fixed the constant of proportionality exactly. A black hole's entropy is 1/4 of its horizon area, measured in units of the Planck area, which is about 2.6 times 10 to the power of -70 square meters. That is a very small tile, and there are a great many of them on the surface of anything. The general principle that grew out of this is called the holographic bound, developed by Gerard Hooft and Leonard Susskind in the 1990s. The maximum information content of any region of space is set by the area of its boundary, not by its volume. A region packed with more information than that limit would collapse into a black hole, which means the bound is not a limitation on our knowledge but a limitation on what can exist. Apply the bound to a region the size of our observable universe, and you get a number. The maximum information that could be contained within our horizon is around 10 to the power of 122 bits. Max Tegmark, then at the Massachusetts Institute of Technology, worked through what that implies. He was not attempting anything provocative. He was following a chain of reasoning that begins with the observational evidence. The universe appears flat. It appears uniform on large scales. And inflation predicts that it extends far beyond our horizon. He published the argument in Scientific American in May of 2003, and it has been sitting in the literature since, largely unrefuted and largely unexamined, because there is very little anyone can do with it. Each of the 10 to the power of 122 bits can take one of two values. The total number of distinguishable configurations of a region our size is therefore 2 raised to that power. Written in base 10, that is roughly 10 raised to the power of 10 to the power of 122. It is not a number that can be usefully compared to anything, because there is nothing to compare it to, but it is finite, and that is the only property required. If the universe is infinite and uniformly filled, then regions the size of ours tile it without end. Each is one draw from a deck of that size. 2. Statistically, you expect to find a duplicate after roughly that many draws, which corresponds to a distance of about 10 raised to the power of 10 to the power of 115 meters. That is the number from the beginning of tonight, and here is the correction that matters, because the two figures get confused constantly. 10 to the power of 10 to the power of 115 meters is the distance to the nearest region, identical to our entire observable universe. Every galaxy in the same place. Every star with the same mass. Every planet with the same history. 46.5 billion light-years of exact duplication in all directions, containing, among a great many other things, a copy of you. The distance to the nearest copy of you alone is much smaller, because the amount of information required to specify one human being is far less than the amount required to specify 46 billion light-years of cosmos. Tegmark's estimate for that is about 10, raised to the power of 10 to the power of 29 meters. The exponent drops from 115 to 29. In ordinary arithmetic, that would be a modest reduction. Here it is a collapse so severe that the two numbers have essentially nothing to do with each other, and yet both are so far beyond any physical scale that the difference has no practical meaning whatsoever. Both are unreachable in the same absolute way. There is a version of this that is harder to dismiss than the exact copies, and it gets less attention. The exact duplicates are extraordinarily rare, buried under those exponents. But near duplicates are not rare. They are common. The same argument that produces one identical region produces vastly more regions that differ in one detail. In one, a single photon that struck your retina 11 minutes ago arrived a fraction of a second later, and a thought went somewhere slightly different. In another, you turned left this morning. In another, a decision you made a decade ago went the other way, and the life that followed diverged completely. These arrange themselves in a kind of gradient around you, from imperceptibly different, through slightly different, through unrecognizable. And because near copies require less information to match, they are much closer. Every degree of similarity has its own characteristic distance, and the more different the version, the nearer the nearest instance of it. The version of you who is asleep already is closer than the version who is identical. Before this gets away from us, the assumptions need stating plainly, because the conclusion is only as good as they are. The argument requires that space be infinite. Flatness is consistent with that and does not establish it. It requires that matter be distributed with roughly uniform statistical properties everywhere, and not just within our horizon, which is an extrapolation of an observed property into a region we cannot observe. It requires that the same laws of physics apply throughout, which is precisely the assumption we will be dismantling in the next section. And it requires that the initial conditions were genuinely random across the full extent of space, rather than correlated in some way that suppresses repetition. Any of these could fail. If inflation produced a universe that is enormously large but finite, the copies might not exist at all, or might exist in far smaller numbers. If the physical constants vary from place to place, the notion of an identical region loses its meaning across most of the volume. Tegmark's own framing is careful in a way that popular accounts of it usually are not. He does not claim to have shown that your duplicate exists. He claims that if the universe is infinite, flat, and statistically uniform, then your duplicate follows as a matter of arithmetic, and there is nothing further to argue about. The physics is in the premises. The conclusion is only counting. What makes this different from ordinary speculation is that it requires no new physics, no extra dimensions, no branching wave function, no exotic particle. It requires only that the universe be large enough, and the evidence we have from the flatness measurements and from inflation says that it very well may be. This is the most conservative of the 5 hypotheses we are looking at tonight. It is the one that asks the least. Tegmark has described his own reaction to working the number out as a kind of vertigo, and it is worth being precise about what produces it. It is not the size of the number, it is the loss of a category. There is a difference between believing that you are one person among 8 billion and believing that you are one instance of a pattern that occurs without limit. The first is a fact about population. The second is a fact about what kind of thing you are. The pattern is real. It is made of matter, in a specific arrangement, doing specific work. It is simply not unique, and the sense that it must be unique turns out to be an assumption nobody ever had grounds for. All of which rests on one premise that we have so far let stand without examination. Every copy in this picture is governed by the same physics, the same electron mass, the same strength of gravity, the same fine structure constant. The argument requires it, because a region where the constants differed would not be a copy of anything here. But there is no known reason why the constants should be the same everywhere. They are measured, not derived. Nothing in any theory we have explains why the electron weighs what it weighs, and the same inflationary mechanism that makes the universe large enough to contain your duplicate turns out, when examined closely, to predict that the constants are not universal at all. That prediction came from a man who was investigating something else entirely, and who wrote 2 words in his notebook in December of 1979. Alan Guth was 32 years old, on his 3rd consecutive postdoctoral position, and running out of time. In the physics of that era, a man who had not secured a permanent post by his early 30s was generally understood to be finished. He had moved from the Massachusetts Institute of Technology to Princeton to Columbia, and then to the Stanford Linear Accelerator Center in California, following short contracts, and he was not working on cosmology. He was working on magnetic monopoles. The monopole problem was this: grand unified theories, which attempt to merge the strong nuclear force with the electromagnetic and weak forces, predict that the early universe should have produced enormous numbers of extremely heavy particles carrying a single isolated magnetic charge. Not a north pole paired with a south pole, as in every magnet anyone has ever handled, but one pole alone. The predicted abundance was comparable to the abundance of protons. If that were correct, monopoles would dominate the mass of the universe and would be turning up in detectors constantly. Not one has ever been found. Guth and a collaborator, Henry Tye, were trying to work out whether some feature of the early universe could have suppressed their production. That was the problem in front of him. The 2 other problems he solved that winter were not problems he had set out to solve, and one of them he had heard of only weeks earlier. The first was the horizon problem, and it is easier to state than to feel the force of. The cosmic microwave background has the same temperature in every direction, to within 1 part in 100,000. 2 patches of sky on opposite sides of us are separated by more than 90 billion light-years. Light has not had time to cross between them since the beginning of the universe. They have never been in contact. Nothing has ever passed from one to the other, and yet they are the same temperature to 5 decimal places. Temperatures equalize by contact. Hot things and cold things brought together exchange energy until they match, and the process requires a physical connection. Regions that have never been connected have no mechanism for matching. At the time the cosmic microwave background was released, a causally connected patch of the universe subtended about 1 degree on our sky, roughly twice the width of the full moon. There are tens of thousands of such patches in the sky, and every one of them agrees with every other one on the temperature, and none of them could have arranged it. The second was the flatness problem. In an expanding universe governed by ordinary matter and radiation, flatness is unstable. Any deviation from the critical density grows over time, in the same way that a pencil balanced on its point does not stay balanced. For the universe to be as close to flat as we observe it to be now, after 13.8 billion years of that instability compounding, the density at very early times must have been equal to the critical density to something like 1 part in 10 to the power of 60. Not approximately, that precisely. There was no explanation for why, and physicists had largely settled into not asking. Guth heard a lecture by Robert Dicke on the flatness problem in November of 1979, and it stayed with him. On the night of the 6th of December, Working late, he saw that a single mechanism dissolved all three. If the very early universe had gone through a brief period of exponential expansion, driven by a field trapped in a high-energy state that behaved like a repulsive pressure, then every one of the puzzles resolved at once. The horizon problem disappeared because the entire observable universe would have originated from a patch small enough to have equalized its temperature before the expansion began. The flatness problem disappeared because stretching any curved surface by a large enough factor makes it locally indistinguishable from flat. And the monopoles disappeared because the expansion would have diluted them so severely that we would expect perhaps one within the entire observable universe. He wrote 2 words in his notebook in capital letters and drew a double box around them. The words were spectacular realization. The next morning, he rode his bicycle to the laboratory in 9 minutes and 32 seconds. He knew the number because he timed the ride regularly and kept a record of it. It was his fastest time. He has mentioned this detail in nearly every interview he has ever given about that week, and it is the most human thing in the entire history of inflationary cosmology. A man solves 3 of the deepest problems in physics in a single evening, and what he remembers with precision is his commute. The mechanism has a name now: inflation. In the standard version, a patch of space roughly 10 to the power of minus 26 meters across, expanded by a factor of at least 10 to the power of 26 in about 10 to the power of minus 32 seconds. The numbers are unhelpful in the way that all numbers at this scale are unhelpful. What matters is the ratio, and the ratio is that something smaller than a proton became larger than a grapefruit, and that this is a larger proportional change than everything that has happened in the 13.8 billion years since. Guth's original model had a fatal defect, which he identified himself and stated openly in the paper. Inflation would end by nucleating bubbles of ordinary space within the inflating region, and those bubbles would need to grow and merge to produce a smooth universe. They could not. The space between them was expanding faster than the bubble walls could advance, so they never coalesced. The result would be a violently inhomogeneous cosmos, nothing like the one we live in. This was called the graceful exit problem, and for 2 years inflation was a beautiful idea that did not work. It was fixed in 1982, independently, by André Linde in Moscow and by Andreas Albrecht and Paul Steinhardt in the United States. Their solution was to have the field roll slowly down a gentle slope in its energy landscape, rather than tunnel abruptly out of a trapped state. Inflation would then end smoothly, everywhere within a bubble, and the energy stored in the field would convert into a hot, dense soup of particles. That conversion is called reheating, and it is what we have historically called the Big Bang. In this picture, the Big Bang is not the beginning. It is the aftermath, the moment the fuel of inflation was dumped into ordinary matter and radiation within one region. Then Linde asked the question that turns a theory of cosmic origins into something considerably larger. Does inflation stop everywhere? The field driving inflation is a quantum field, and quantum fields fluctuate. As the field rolls down its slope toward the value where inflation ends, random quantum jumps push it back up in some regions and further down in others. In the regions where it is pushed down, inflation ends and a bubble of ordinary space forms. In the regions where it is pushed back up, inflation continues. And here is the part that changes the picture entirely. The regions where inflation continues are expanding exponentially. The regions where it has stopped are expanding only at ordinary rates. So the inflating volume grows far faster than it is consumed by the bubbles forming within it. No matter how many bubbles nucleate, the space available for new bubbles grows faster still. The process cannot run out. It has no natural end. Linde called this eternal inflation. Alexander Vilenkin at Tufts University reached the same conclusion independently at almost the same time. Inflation, once started, continues forever in most of the volume of the universe, and it produces bubbles without limit. Our entire observable universe, everything in the previous 3 sections, all 46.5 billion light-years of it, is the interior of one bubble. The bubbles cannot meet. Their walls advance at nearly the speed of light, but the inflating space between any 2 bubbles stretches faster than that, so the gap between them grows even as both expand. Each bubble is, for anything inside it, a complete and self-contained universe with no accessible exterior. That would be strange enough as a piece of geometry. What makes it consequential is what happens to the physics inside each bubble. In string theory, the fields that determine the properties of our universe are related to the geometry of extraspatial dimensions, curled up too small to observe. The number of stable ways those dimensions can be configured is not small. Estimates, published by Raphael Bousseau and Joseph Polchinski in the year 2000, and developed by Leonard Susskind in a paper in 2003 that gave the idea its name, put the number of distinct stable configurations at something like 10 to the power of 500. Susskind called it the landscape. Each configuration corresponds to a different vacuum state, and each vacuum state has its own low-energy physics, different particle masses, different force strengths, different value for the energy density of empty space. When a bubble nucleates, the field settles into one of those configurations, and the physics inside that bubble is fixed for its entire history by which one it landed in. In most of them, nothing interesting can happen. If the electron was slightly heavier relative to the proton, stable atoms would not form. If the strong nuclear force were a few percent weaker, carbon could not exist. If the energy density of the vacuum was substantially larger, space would have torn itself apart before any structure could condense out of it. The overwhelming majority of the landscape is sterile, not because of any hostility, but because the numbers do not permit chemistry. There is one piece of evidence for this framework that is genuinely hard to dismiss, and it takes the form of a successful prediction made 11 years before the relevant measurement. In 1987, Steven Weinberg published a paper on the cosmological constant. The theoretical prediction for the energy density of the vacuum, calculated from quantum field theory, exceeds the observationally allowed value by something like 120 orders of magnitude. This is routinely described as the worst quantitative prediction in the history of physics, and the description is fair. Everyone assumed there must be some undiscovered symmetry forcing the value to be exactly zero. Weinberg asked a different question. Suppose the value varies across a large ensemble of regions. What values are compatible with the existence of observers? If it were large and positive, space would expand too fast for galaxies to form, and there would be nobody to measure it. If it were large and negative, the universe would recollapse before life could arise. The window is narrow. Weinberg calculated the upper end of the window and predicted that if the constant is not zero, it should be small but non-zero, within a couple of orders of magnitude of the density of matter at the time galaxies formed. In 1998, the value was measured. It is not zero. It falls within the range Weinberg identified. This does not prove the multiverse. There are other possible explanations, and many physicists find the reasoning unsatisfying because it explains a number by reference to our own existence rather than by deriving it. But it is a prediction that was written down in advance and that came out right, and there are not many of those in this part of physics. The obvious question is whether any of it can be tested more directly, and there is one place to look. If our bubble ever collided with a neighbouring bubble in the early universe, before inflation drove them apart, the collision would have left a permanent scar. Specifically, it would produce a circular disk on the sky of slightly different temperature, with a sharp edge and a distinctive polarization signature. In 2004, an unusually large and cold region was identified in the microwave background data, about 5 degrees across and roughly 70 millionths of a Kelvin cooler than its surroundings. It became known as the cold spot. In 2006, the astrophysicist Laura Mersini-Houghton proposed that it was exactly such a scar, the bruise left by contact with another universe. The claim received a great deal of attention. The subsequent history is instructive. A team led by Stephen Feeney published a systematic search for bubble collision signatures across the entire sky in 2011 and found no statistically significant detections. The Planck satellite, with substantially better resolution and sensitivity, examined the cold spot and concluded it is consistent with the ordinary random fluctuations the standard model predicts. Rare, but not rare enough to require an explanation. A separate proposal, that the cold spot is the imprint of an enormous underdense region of space between us and the microwave background, was advanced in 2015 and has itself been disputed since. The bubbles, if they exist, remain silent. They are sealed off by the same expansion that produced them. Linda has described what eternal inflation does to our position as a kind of Copernican revolution, applied a second time. Copernicus moved the Earth out of the centre. Shapley moved the Sun out of the centre of the galaxy. And then, Hubble established that our galaxy is one among an enormous number. Eternal inflation removes the last special status remaining, which is the assumption that the laws we measure are the laws. The constants of nature that were measured over 4 centuries, refined, tabulated, and treated as the bedrock properties of reality, would in this picture be local conditions. The mass of the electron would not be a cosmic quantity. It would be a fact about our neighbourhood, no more fundamental than the average rainfall of a particular valley, which leaves a specific and uncomfortable gap in what physics can be expected to deliver. If the constants are accidents of which vacuum our bubble fell into, then the project of deriving them from first principles is not merely difficult, it is impossible in principle, and every hour spent on it is wasted. There is no consensus on whether that is true, and the disagreement is not polite. There is also a second kind of multiplication implied here, and it does not require inflating space or extra dimensions at all. The bubbles give you different laws in different places, but something in the mathematics of quantum mechanics has been suggesting, since the 1950s, that there is a far more intimate branching happening continuously. Everywhere, including in the room where you are lying right now. The man who worked it out was 27 years old, and he was told to make his thesis shorter. The problem Hugh Everett attacked had been sitting at the centre of quantum mechanics for 30 years, and the standard response to it was to look somewhere else. Quantum mechanics describes a system by a mathematical object called the wave function, which evolves smoothly and deterministically according to the Schrödinger equation. Given the wave function now, the equation tells you the wave function later, with no ambiguity and no randomness whatsoever. The theory is, at that level, as rigidly determined as Newtonian mechanics. But the wave function does not describe a single definite state. It describes a superposition, a weighted combination of every possible state the system could be in. An electron does not have a definite spin direction. It has a wave function that includes both. And when you measure it, you never observe a superposition. You observe one outcome. The Copenhagen interpretation, assembled largely by Niels Bohr and Werner Heisenberg in the 1920s, handled this by adding a second rule. The wave function evolves smoothly according to the Schrödinger equation until a measurement occurs, at which point it collapses instantaneously and randomly to a single outcome, with probabilities given by the square of the amplitudes. 2 rules, one deterministic and continuous, one probabilistic and instantaneous. The theory does not say what triggers the switch between them. It does not define what counts as a measurement, or where the boundary lies between the quantum world that superposes and the classical world that does not, or why an apparatus made entirely of atoms obeying the first rule should be governed by the second. Bohr's position was, in essence, that these questions were malformed, and that the theory's job was to predict experimental outcomes, which it did with unmatched accuracy. It was, and remains, the most successful calculational framework ever devised. It is also, as a description of what is happening, an evasion, and Everett was not the first person to notice. He was the first to publish a serious alternative. The idea appears to have originated at a party. In 1954, Everett was a graduate student at Princeton, and he was drinking sherry with a fellow student named Charles Misner and with Arge Peterson, who was Bohr's assistant and was visiting. The conversation turned to the absurdities of the measurement problem. Everett later said the idea came to him that evening, in the middle of an argument, and that alcohol was involved. His proposal was to delete the second rule. That is the whole of it. Do not add anything. Remove the collapse postulate and keep only the Schrödinger equation, applied universally to everything, including observers and measuring devices and the entire universe as a single quantum system. Follow that through and the consequences are immediate. When an apparatus measures an electron in a superposition of 2 spin states, the apparatus does not force a choice. It becomes entangled with the electron, and the combined system is now in a superposition of 2 states. Apparatus reading up with electron spin up, and apparatus reading down with electron spin down. When a person looks at the apparatus, the person becomes entangled too. The superposition now includes 2 versions of the observer, each with a definite memory of a definite result, each entirely unaware of the other. Neither one is the real one. There is no mechanism in the mathematics for selecting between them, because the mechanism for selecting between them was the thing that got deleted. Everett's original thesis ran to 137 pages. Wheeler, who supervised him, called the work brilliant and was also acutely conscious of what Bohr would think of it. Bohr was 72, universally revered, and the intellectual architect of the interpretation Everett was proposing to discard. Wheeler required extensive revisions, and the version published in Reviews of Modern Physics in July of 1957 ran to 9 pages, with the philosophical argument largely removed and the language softened throughout. Everett titled it The Relative State Formulation, which is accurate and describes the central technical insight and which conveys none of what the paper actually claims. In March of 1959, Everett travelled to Copenhagen to present the idea to Bohr in person. He stayed 6 weeks. The substantive discussion lasted, by his own later account, about an hour and a half and achieved nothing. Peterson, who had been present at the original Sherry conversation, said afterwards that the visit had been doomed before it started. Bohr was not going to entertain the removal of his interpretation from quantum mechanics, and there was no version of the meeting in which he would have. Everett went home and left physics. He took a position with the Weapons Systems Evaluation Group at the Pentagon, working on the mathematics of nuclear war. He built optimization models for targeting strategies and for the evaluation of fallout. He was, by all accounts, extremely good at it. He later founded his own defense consulting company. He was a heavy smoker, drank steadily, ate badly, and did not exercise. He published no further physics. The revival came from Bryce DeWitt at the University of Texas, who had initially written to Everett objecting that he did not feel himself splitting. Everett's reply pointed out that Copernicus faced the same objection. Nobody feels the Earth moving either. DeWitt found this persuasive. He wrote an article for Physics Today in 1970 that presented the interpretation to a broad audience for the first time, and he gave it the name that stuck, Many Worlds. Everett disliked the name for the rest of his life. It suggested separate places, which is precisely what the theory does not describe. The technical piece that made the interpretation respectable rather than merely provocative arrived through work on decoherence, developed by Dieter Zeh in Heidelberg from 1970 and considerably extended by Wojciech Zurek from the early 1980s. Decoherence explains why the branches do not interfere with each other. A quantum system in isolation maintains its superposition, and the parts of the superposition can recombine and produce interference effects, which is what the double-slit experiment demonstrates. But no system is isolated. Every object is constantly bombarded by air molecules, thermal photons, the microwave background itself. Each interaction entangles the object a little further with its environment, and the information distinguishing one branch from another leaks outward into an ever-increasing number of particles. The information is not destroyed, it is dispersed, and once it is spread across enough degrees of freedom, recombining the branches becomes not merely difficult, but so improbable that it will not occur in the lifetime of the universe. The branches become effectively independent. Each evolves as though it were the only one, and any observer inside one sees a single, consistent classical world. Zurek calculated timescales, and they are the reason this feels the way it does. A dust grain 1/100th of a millimeter across, floating in air, decoheres in something like 10 to the power of minus 31 seconds. Even in the best laboratory vacuum, illuminated only by the cosmic microwave background, the same grain decoheres in about a second. There is no possibility of experiencing the branching. It is finished before any nervous system could register it. David Deutsch at Oxford has argued that the interpretation is not merely defensible but forced, and his argument comes from quantum computing rather than from philosophy. A quantum computer running Shor's algorithm can factor a large number into its primes exponentially faster than any known classical method. To factor a number of a few thousand digits, the computation would require a number of interfering computational paths vastly greater than the number of atoms in the observable universe. Deutsch's question is simply where that computation is performed. The physical device is small. It sits on a bench. If the number of distinct calculations being carried out exceeds by an enormous factor the number of particles available in the visible universe to carry them out, then, in his view, the resources must be somewhere, and the only candidate the mathematics offers is the other branches. He has put the point bluntly: when a quantum computer gives you an answer, ask the people who deny the existence of the other worlds where the calculation was done. Not everyone accepts this, and the objections are real. The most serious technical criticism concerns probability. If every outcome occurs, what does it mean to say that one outcome has a 70% chance? 70% of what? Deutsch proposed a derivation of the probability rule from decision theory in 1999, and David Wallace developed it substantially, and the debate over whether it succeeds is ongoing and technical. A second objection concerns why the branches divide along the particular lines they do rather than along some other mathematically equivalent division. Decoherence provides much of the answer, and it is not clear that it provides all of it. Where it stands is that many worlds is a serious minority position rather than a curiosity. A poll conducted at a Foundations of Quantum Mechanics conference in 2011 found 42% of participants favouring some form of Copenhagen and 18% favouring many worlds. The sample was small and the participants self-selected, and the result should not be overread, but a fringe idea does not draw 18% at a specialist conference. Everett did not live to see any of this settle. He died on the 19th of July, 1982, of a heart attack at the age of 51. His wife found him in bed. In accordance with instructions he had given, his ashes were disposed of with the household waste. His widow kept them in a filing cabinet for several years first, apparently unable to carry out the request, before doing it. His daughter Elizabeth said her father had believed his interpretation so completely that he found it consoling. He had told the family that death in one branch simply meant continuing in the others, and that a version of him would always survive. She struggled for most of her life with depression. In 1996, she took her own life, and the note she left said that she was going to a parallel universe to be with her father. His son, Mark Oliver Everett, grew up knowing almost nothing about his father's work. He was 15 when he found the body. He became a musician, the frontman of the band Eels, and in 2007 he made a documentary in which he tried to understand what his father had done. He travelled to Princeton, met physicists who revered a man he remembered as silent and unreachable, sat in the house he had grown up in, and looked at the equations. The film does not resolve into anything. He does not come to understand the physics, and he says so. What he finds is that a great many strangers have thought carefully about his father, and that he is not one of them, and that this is now permanent. The most a person can do with a fact like that is to look at it. So we have 3 multiverses, and they do not overlap. Cosmic repetition gives duplicates far away in space, under identical laws. Eternal inflation gives different laws in bubbles we can never reach. Many worlds gives divergent histories in the same space, separated not by distance, but by decoherence. All 3 share a property that should be stated plainly, because it is the standard objection and it is a fair one. Not one of them can be observed. Bubbles cannot be contacted. Branches cannot be recombined. Regions beyond the horizon cannot send signals. Each theory arrives, by its own internal logic, at the conclusion that its predictions are unreachable, except that there is one measurement that does not fit the standard picture. It has been sitting in the literature since 2008, contested and unresolved. It concerns the motion of several hundred galaxy clusters, and it points to a specific patch of sky. It is not an abstraction. It is a direction and a speed. Before the anomaly, there is a motion that is not anomalous at all, and it needs establishing first because everything else is measured against it. The cosmic microwave background is not perfectly uniform. One half of the sky is very slightly hotter than the other, by about 1 part in 1,000, in a smooth gradient from one pole to the opposite one. This is far larger than the tiny fluctuations we discussed earlier, and it has a mundane explanation. We are moving. The solar system is travelling through the universe at about 370 kilometers per second, and the radiation ahead of us is blue-shifted while the radiation behind is red-shifted. The pattern is called the dipole, and once you subtract it, the remaining variations are the primordial ones. That motion is itself a composite. The Earth orbits the Sun. The Sun orbits the centre of the Milky Way at about 220 kilometers per second. The Milky Way falls toward the Andromeda galaxy. The local group falls toward the Virgo cluster. Virgo falls toward something further still. Each layer adds a vector, and the sum is what the dipole measures. Astronomers have known for decades that the largest component of that fall points toward a region in the direction of the constellations Centaurus and Hydra, obscured behind the plane of our own galaxy, where dust and stars block the view. In the 1980s, a group of astronomers who became known as the Seven Samurai mapped these motions and identified a concentration of mass in that direction, which they named the Great Attractor. It sits about 250 million light-years away. Later work showed that a substantial part of the pull actually comes from further out, from the Shapley supercluster at roughly 650 million light-years, the densest known concentration of galaxies in the nearby universe. In 2014, a team led by Brent Tully and Helene Courtois mapped these flows in far greater detail and showed that the Milky Way sits at the outer edge of a single enormous structure defined by the pattern of motion within it, 520 million light-years across, containing perhaps 100,000 galaxies. They named it Laniakea, from Hawaiian words meaning immeasurable heaven. 3 years later, some of the same researchers identified a complementary structure, a vast underdense region on the opposite side of the sky, pushing rather than pulling, which they called the dipole repeller. Half of our motion is being attracted. The other half is being left behind by a region that has less than its share of matter. All of this is standard cosmology working correctly. Structures form, gravity pulls, galaxies acquire motions on top of the general expansion. These extra motions are called peculiar velocities, and in the standard model they should be a few hundred kilometers per second at most, and they should become smaller as you look at larger volumes, because on sufficiently large scales the universe averages out to uniformity, and there is nothing left to pull toward. That last expectation is the one that came under question. Alexander Kashlinsky is an astrophysicist at the Goddard Space Flight Center in Maryland, known within his field for meticulous work on faint infrared backgrounds. He is not a theorist, and he has spent very little of his career making claims about the structure of reality. In 2008, with 3 collaborators, Fernando Atrio-Barandella, Daniel Kachevsky, and Harold Eberling, he published a short paper in the Astrophysical Journal Letters describing a measurement that his field has been arguing about ever since. The technique depends on an effect predicted in 1972 by 2 Soviet physicists, Rashid Sunyaev and Yakov Zeldovich. Galaxy clusters are the largest structures held together by gravity. A large one contains 1,000 galaxies or more, but most of its ordinary matter is not in the galaxies at all. It is in a thin plasma filling the space between them, heated by gravitational compression to tens of millions of degrees. The gas is so diffuse that a cubic meter of it contains fewer particles than the best vacuum achievable on Earth, and yet the cluster contains so much volume that this gas outweighs all the stars in all its galaxies combined. When a photon from the cosmic microwave background passes through that plasma, it has a small chance of colliding with one of the fast-moving electrons. The electron is far more energetic than the photon, so energy flows the wrong way compared to ordinary scattering. The photon gains energy and shifts to a higher frequency. Across the whole population of photons passing through the cluster, this produces a characteristic distortion, a deficit at low frequencies and an excess at high ones. This is the thermal effect, and it is now a standard tool. Because it depends on the amount of gas rather than on distance, a cluster produces the same signature whether it is nearby or extremely far away, which makes it an unusually democratic way of finding them. There is a second, much fainter version. If the cluster as a whole is moving relative to the background radiation, the scattered photons pick up an additional shift from that bulk motion, in the same way that the dipole arises from our own. This is the kinematic effect. It is roughly 10 times weaker than the thermal effect. It has no distinctive spectral shape to separate it out, and detecting it in a single cluster is beyond current instruments. Kashlinsky's approach was to give up on single clusters and measure the population. He assembled a catalogue of several hundred clusters with well-determined positions and gas properties, filtered the microwave background data to suppress the primordial fluctuations, and added the signal at all cluster positions together. If the clusters move randomly, the individual shifts point in random directions and cancel. If they share a common motion, the shifts reinforce and a residual survives. A residual survived. The clusters, as a population, appeared to be moving together toward a region of sky between Centaurus and Vela at a speed somewhere between 600 and 1,000 kilometers per second. The flow did not weaken with distance. It persisted in clusters out to at least 2.5 billion light-years. In 2010, using the 5-year data from the Wilkinson microwave anisotropy probe and a sample expanded past 1,000 clusters, the team reported the same direction and the same amplitude, extending further still. The standard model does not permit this. On scales of billions of light-years, the predicted coherent motion is under 200 kilometers per second, and it should fall off as the volume grows. A flow of 1,000 kilometers per second, unchanged across 2.5 billion light-years, would mean the pull is coming from outside the region being surveyed. Push the survey far enough and the source has to lie beyond the horizon. Kashlinsky called it the dark flow. The name was a mistake in terms of how the result was received, since it invited immediate comparison with dark matter and dark energy, and implied a confidence the paper did not claim. The field split. Some cosmologists found the analysis careful and the result provocative. Many were skeptical, and their skepticism was methodological rather than philosophical. The kinematic signal is buried under a thermal signal 10 times larger, and under primordial fluctuations larger still. Extracting it requires assumptions about the gas temperature and distribution in every cluster, an aggressive filtering procedure, and a careful treatment of correlated errors. Small mistakes in any of those steps can manufacture a signal that is not there. Several independent groups reanalyzed similar data and reported no detection. In 2013, the Planck collaboration published its own analysis. Planck had better angular resolution and lower noise than its predecessor, and it had detected a large sample of clusters itself through the thermal effect, so the cluster catalogue and the background map came from the same instrument. Their conclusion was an upper limit rather than a detection. Any coherent motion on scales above about 3 billion light-years is below 254 kilometers per second. In their data, there is no dark flow. Kashlinsky's response was technical and specific. He argued that the Planck filtering procedure, optimized for detecting the thermal effect, removes much of the kinematic signal along with the noise, and that the cluster sample was selected in a way that reduces sensitivity to exactly the scales in question. The Planck team maintained that their treatment was appropriate and their errors better characterized. Both sides have published further rounds. Neither has conceded. It matters that this is not an isolated dispute. There is a separate and largely independent line of evidence for anomalous large-scale motion that does not use the microwave background at all. It measures peculiar velocities directly by comparing the distance to a galaxy inferred from its intrinsic properties with the distance inferred from its redshift, and attributing the difference to motion. In 2009, Richard Watkins, Hume Feldman and Michael Hudson analysed a compilation of such measurements and found a bulk flow of about 400 kilometers per second within a radius of 325 million light-years, which is larger than the standard model comfortably accommodates. In 2023, using the substantially larger Cosmic Flows catalogue, Watkins and collaborators reported that the bulk flow at larger radii exceeds the standard prediction by a wide margin, in some measures by more than 4 standard deviations. These results do not confirm the dark flow. They probe smaller scales, use entirely different methods, and carry their own systematic uncertainties. What they establish is that the question of whether large-scale motions match prediction is genuinely open, and that the disagreement is not confined to one contested technique. If a flow of the kind Kashlinsky reported is real, the possible causes are limited and none of them are comfortable. The pull could come from a concentration of matter beyond the observable horizon, a structure so large that nothing comparable exists within our view. It could be a remnant of conditions before inflation, a large-scale gradient, that inflation stretched to a size exceeding our horizon rather than erasing. This possibility was examined theoretically well before the measurement, under the name of a tilted universe, and it predicts approximately what was reported, or A. In the most speculative reading, it could be the gravitational influence of a neighbouring bubble universe, close enough in the earliest moments that its gravitational field still reaches across, even though its light and matter never can. Kashlinsky himself has been consistently reluctant to endorse any of these. His public statements have stayed close to the data. Something appears to be moving, Motion requires a cause, and the cause does not appear to lie within the volume surveyed. He has said that if the result holds, the standard cosmological model would need re-examination, and he has not gone further than that. Resolution is possible, and it may not be far off. The South Pole Telescope and the Atacama Cosmology Telescope both measure the Sunyaev-Zeldovich effect at higher resolution than any satellite, over smaller patches of sky. Large spectroscopic surveys are producing cluster catalogues, an order of magnitude larger than the ones Kashlinsky used. The measurement that settles this has not been made, but it is the kind of measurement that gets made. What is worth holding on to is the shape of the situation rather than its outcome. Every other route to the region beyond the horizon has been closed by construction. Bubbles cannot be reached because the space between them expands too fast. Branches cannot be reached because decoherence has scattered the information irretrievably. Distant duplicates cannot be reached because the light will never arrive. Gravity is different. Gravity does not respect the horizon in the same way. A mass distribution set up before inflation leaves a gradient, and that gradient does not need a signal to cross the gap. It is already here, imprinted in the initial conditions, expressing itself as a slow drift in the objects we can see. If there is ever any observational contact with what lies outside, this is the shape it will take. Not an image, not a message, a direction and a speed, and an argument that lasts 20 years about whether the measurement is sound. Which leaves one more question about the outside, and it is the one that sounds simplest and is not. The dark flow, if it is real, is a motion towards something. But most of what lies beyond the horizon, on any of these pictures, is not a structure at all. It is space, emptiness. And it turns out that we do not have a clear idea of what emptiness is. Take a sealed container and remove the air. Then cool it until every atom left inside has settled to its lowest possible energy. Then remove the radiation, shielding it so completely that not a single photon enters or leaves. What remains inside the container is the closest thing to nothing that can exist within our universe. It is not empty, and the amount by which it is not empty can be measured to 11 decimal places. Quantum field theory, the framework underlying all of particle physics, describes the universe not as a collection of particles but as a set of fields extending through all of space. Particles are excitations of those fields, localized disturbances that behave like objects. The electron field fills the room you are lying in. So does the photon field, and the quark fields, and all the rest. They are present everywhere, including when nothing is happening. A field cannot be perfectly still. This is the uncertainty principle applied to fields rather than to particles. A field with exactly zero value and exactly zero rate of change would be specified too precisely for quantum mechanics to allow. So every field retains a residual jitter, an irreducible minimum activity, even in its lowest energy state. This is called zero-point energy, and it is not an approximation or a modeling convenience. It is the ground state of reality, and it has consequences that can be checked. The most striking of these was predicted by a Dutch physicist working in industry. Hendrik Casimir was employed at the Philips Research Laboratories in Eindhoven, where his assignment involved the stability of colloidal suspensions in products the company sold. Working with Dirk Polder, he had derived a correction to the known attractive forces between neutral molecules. The result was correct, but the derivation was laborious, and its simplicity of form suggested that something was being missed. In 1947, he described the work to Niels Bohr during a walk. Bohr listened, and then said, in a mumble that Casimir recorded carefully, that it was nice and new, and that Casimir ought to try thinking about it in terms of zero-point energy. Casimir did, and within a year he had produced a prediction of striking simplicity. Take two flat conducting plates, uncharged, and place them parallel in a vacuum, with a very small gap between them. The electromagnetic field between the plates is constrained. Only wavelengths that fit a whole number of times into the gap can exist there. Outside the plates, all wavelengths are permitted. So there are fewer field modes between the plates than outside, and therefore less zero-point energy per unit volume between them. The imbalance produces a net inward pressure. The plates are pushed together by the vacuum. The force depends on the fourth power of the separation, which means it is negligible at ordinary distances and becomes dramatic at very small ones. For plates separated by 10 nanometers, roughly 100 atomic diameters, the Casimir pressure is comparable to the pressure of the atmosphere at sea level. For plates a micron apart, it is about 100,000th of that, which is why the effect took half a century to measure. The first convincing measurement was made by Steve Lamoureux at the University of Washington in 1997. He used a torsion pendulum, a horizontal bar suspended on a fine fiber with the deflection read out electronically. Rather than two flat plates, which must be held perfectly parallel to an impossible tolerance, he used a sphere close to a flat plate, a geometry that removes the alignment problem while producing a predictable force. He measured agreement with Casimir's prediction to within 5%. The following year, Umar Mohideen and Anushree Roy used an atomic force microscope to push the agreement to about 1%. In 2011, a group at Chalmers University in Sweden went further and produced photons out of the vacuum directly. The principle had been predicted decades earlier. If you move a mirror at a speed approaching the speed of light, the vacuum fluctuations cannot adjust fast enough, and some of the virtual photons are converted into real ones that can be detected. Moving a physical mirror that fast is not possible. Instead, the team built a superconducting circuit whose electrical properties could be varied billions of times per second, producing a boundary condition that moved effectively at about a quarter of the speed of light. Photons came out. They were measured, and their statistical properties matched the prediction for photons generated from vacuum fluctuations rather than from thermal noise. Zero-point energy also shows up in the most precisely verified prediction in the history of science. The magnetic moment of the electron differs slightly from the simplest theoretical value because the electron continuously interacts with the fluctuating fields around it. Quantum electrodynamics predicts the size of that correction. Experiment measures it. The two agree to roughly 12 significant figures. Nothing else in physics is confirmed to that precision, and the calculation that achieves it is a calculation about the structure of empty space. So the vacuum is a physical medium. It has structure, it responds to boundaries, it produces measurable forces, and it can be made to emit light. Which brings us to the largest unsolved problem in theoretical physics. And it is a problem precisely because the vacuum is real. Add up the zero-point energy of all the fields, and you get an energy density for empty space. Empty space with an energy density gravitates. And in general relativity, a uniform energy density that does not dilute as space expands acts as a repulsive pressure. It drives acceleration. So the vacuum energy should show up directly as the cosmological constant. We have measured the cosmological constant. It corresponds to an energy density equivalent to about 10 to the power of minus 29 grams per cubic centimeter, which is roughly the mass of a few hydrogen atoms spread through a cubic meter. Extremely small. The theoretical calculation exceeds the measured value by something in the region of 120 orders of magnitude. This is not a case of a rough estimate being off. It is the largest discrepancy between prediction and observation anywhere in physics, and no one has explained it. The plainest reading is that the theory is missing a mechanism that cancels the vacuum energy almost perfectly, and then stops just short of cancelling it completely. And nobody knows what that mechanism could be or why it would leave a residue. That is the vacuum inside our universe. There is a deeper sense of nothing that our physics cannot address at all. Everything described so far assumes the existence of space and time as a stage on which fields fluctuate. Remove the stage. Not empty space, but the absence of space. No geometry, no distance, no duration, no location at which anything could be said not to be happening. This is not a colder or emptier version of a vacuum. It is a state for which our equations have no variables. There are attempts. In 1973, Edward Tryon published a short paper in Nature asking whether the universe might be a vacuum fluctuation. His observation was that the positive energy of all matter and radiation may be exactly cancelled by the negative energy of the gravitational field binding it together, so that the total energy of the universe is zero. A quantum fluctuation is limited in magnitude and duration by the uncertainty principle, but a fluctuation of exactly zero total energy is subject to no such limit and can persist indefinitely. Tryon later said the idea came to him during a seminar, that he said it aloud, and that the room laughed. In 1982, Alexander Vilenkin produced a more developed version, in which a closed region of space-time tunnels quantum mechanically from a state with no classical geometry into an inflating one. The initial state in Vilenkin's model is not a pre-existing empty space waiting for something to happen. It is a condition without definite geometry at all. A year later, James Hartle and Stephen Hawking proposed a related construction in which time behaves as a fourth spatial dimension near the beginning, so that the universe has no initial boundary and no first moment, in the way that the surface of the Earth has no southernmost point. These are serious proposals published by serious physicists, and they are not testable in any way currently imaginable. They should be held loosely. What is testable is the emptiest region we can actually observe, and it is worth ending on because it is not an abstraction. In 1981, Robert Kirshner and colleagues, surveying galaxy redshifts in the direction of the constellation Bootes, found a region roughly 330 million light-years across, containing almost no galaxies. It has perhaps 60, where a comparable volume elsewhere would hold 10,000. A galaxy in the middle of it would have had no visible neighbours at all through most of the 20th century, with the nearest other galaxies too faint and too far to detect. Astronomers occasionally note that if the Milky Way sat at the centre of the Bootes void, we would not have known other galaxies existed until well into the 1960s. Put yourself inside it, in the middle, and consider what is missing. There is no sun, there is no sky in any meaningful sense, because a sky requires something overhead. Look in any direction, and the nearest galaxy is more than 150 million light-years away, which means it is a smudge below the threshold of any unaided eye and most equipment. There is no wind, no sound, no pressure, no up or down. The nearest atom to the one in front of you is, on average, more than a meter away, and yet it is not empty. The electron field is there, and the photon field, and the rest, holding their irreducible jitter. The vacuum energy is there, pushing the void slowly wider, which is why voids grow. The microwave background is there, passing through, cooling. If you set two conducting plates a few nanometers apart in the deepest part of the Bootes void, they would be pushed together by exactly the same force that Casimir predicted and Lamoureux measured, because that force does not come from anything in the room. It comes from what the room is made of. The emptiest place we have found is not nothing. It is the same physical medium as everywhere else, with almost all of the furniture removed. Inside that void, the density of ordinary matter is a fraction of an atom per cubic meter. But the fields are still there, the vacuum energy is still there, pushing the void wider. The cosmic microwave background still passes through it, redshifted and cooling, currently at 2.725 Kelvin. That temperature is not stable. It has been falling since the beginning, and it will continue to fall as long as the universe expands, halving with every doubling of the scale factor, approaching absolute zero without ever arriving, which points at something the last few sections have circled without naming. The universe is not only larger than we can see, it is going somewhere. The expansion that hides the duplicates and separates the bubbles is accelerating, and acceleration has a destination. The discovery that it is accelerating was made by two teams who were both looking for the opposite result, and who both spent months trying to find the error in their own data. In the early 1990s, the open question in cosmology had a comfortable shape. Everyone agreed the universe was expanding, and everyone agreed the expansion was slowing down, because gravity pulls and there is nothing else. The only question was by how much. If the deceleration was strong enough, expansion would eventually halt and reverse, ending in a collapse. If it were not, the universe would expand forever at an ever more sluggish rate, coasting towards stillness. Measure the deceleration, and you have the fate of everything. Two groups set out to measure it, and they did not like each other much. The tool for the job was a particular kind of exploding star. A white dwarf is the exposed core left behind when a star like the Sun exhausts its fuel, an object about the size of the Earth containing most of the mass of a star, held up not by heat but by the resistance of its own electrons to being pushed closer together. There is a limit to how much mass that resistance can support, calculated by Subramanian Chandrasekhar in 1930 at the age of 19, on a boat from India to England. The limit is about 1.4 times the mass of the Sun. If a white dwarf in a binary system pulls material from its companion and creeps toward that limit, it does not gradually collapse. It detonates, consuming itself in a runaway thermonuclear reaction that briefly outshines the entire galaxy around it. Because the explosion is triggered at the same mass every time, The energy released is nearly the same every time. That makes it a standard candle, an object whose true brightness is known, so that its apparent brightness reveals its distance. Nearly the same is not the same, and the residual variation was the obstacle. It was solved in 1993 by Mark Phillips, working in Chile, who found that the variation is not random. Brighter explosions fade more slowly. The shape of the light curve predicts the peak luminosity. Measure how quickly the supernova dims over the weeks after its peak, apply the correction, and the scatter collapses to a few percent. Phillips turned a rough tool into a precise one, and everything that followed depended on it. The Supernova Cosmology Project, based at the Lawrence Berkeley Laboratory and led by Saul Perlmutter, we had been running since the late 1980s and had spent years on a problem that sounds administrative and was not. Supernovae are unpredictable. Time on the world's largest telescopes is allocated months in advance. You cannot apply for observing time to study an event that has not happened yet, and may not happen at all. Perlmutter's group solved this by developing a batch strategy. Photograph large fields of sky just after a new moon, photograph the same fields 3 weeks later, subtract the images, and any new point of light is a candidate. By scheduling the second observation immediately before their allocated time on a large telescope, they could effectively guarantee a supply of fresh supernovae to observe. It made the science possible, and it took most of a decade to get right. The High Z Supernova Search Team formed in 1994, led by Brian Schmidt, then in his late 20s and working in Australia, with Adam Rees handling much of the analysis. They used similar methods and pursued the same goal, and the competition between the two groups was intense enough that participants have described it, years later, and with the softening of hindsight, as unpleasant. Both teams expected to measure how much the expansion had slowed. If it had, distant supernovae would appear slightly brighter than a constant expansion rate predicts, because the universe would have been expanding faster when the light was emitted, placing the source closer than a naive calculation suggests. In the autumn of 1997, Rees ran the analysis on his team's accumulated data and got a negative mass density for the universe. That is not an unusual result. That is an impossible result. Mass density cannot be less than 0. He assumed he had made an error and went looking for it. He did not find it. Turning the calculation around and allowing for a cosmological constant, the data fit perfectly and said the expansion was accelerating. Schmidt has described his reaction on being shown the result as sitting somewhere between amazement and horror. Both teams did what a competent scientist does with an answer they do not believe. They attacked their own work. Dust in the host galaxies could dim distant supernovae and mimic the effect, so they checked the colours, because dust reddens and simple distance does not. They considered whether supernovae in the early universe might be intrinsically fainter due to a different chemical composition in the progenitor stars, and examined the spectra for evidence. They looked for selection effects in how the distant events were discovered. Nothing removed it. The distant supernovae were dimmer than they should be, which meant they were further away than they should be, which meant the expansion had been slower in the past than it is now. Perlmutter's team presented first, at a meeting in January of 1998. Schmidt and Rees's team submitted their paper in September. The two analyses were independent, used different supernovae, different software, and different people who were not sharing results, and they agreed. Michael Turner supplied the name for whatever was driving the acceleration, and the name was dark energy, chosen partly for its resonance with dark matter and partly because it committed to nothing. Perlmutter, Schmidt, and Rees received the Nobel Prize in 2011. The accounting of the universe had to be rewritten. Everything made of atoms, every star, every planet, every cloud of gas, everything any telescope has ever imaged, amounts to about 5% of the total energy content. Dark matter, which we detect only through gravity, is about 27%. The remaining 68% is dark energy. Its defining property is that it does not thin out. Ordinary matter dilutes as space expands. The same number of atoms in a growing volume means falling density. Dark energy does not behave that way. Its density stays constant as space grows, which means the total amount increases in step with the volume. It is, on the simplest interpretation, a property of space itself, so more space means more of it. This is why the acceleration is not a phase. Matter dilutes and its gravitational braking weakens. Dark energy does not dilute and its push does not weaken. The ratio between them has already tipped, roughly 5 billion years ago, and it tips further every year. The universe is not slowly coasting to a stop, it is picking up speed permanently. How permanently depends on a single number, the ratio of dark energy's pressure to its density. For a pure property of the vacuum, that ratio is exactly -1, and the acceleration continues at a steady exponential rate forever. 25. If the ratio were somewhat more negative than -1, the acceleration would intensify without limit and eventually tear apart galaxies, then stars, then atoms, in a scenario called the Big Rip. Measurements have consistently placed the value within a few percent of -1, which is what a plain cosmological constant predicts. That consistency has recently come under some pressure. Results from a large spectroscopic survey mapping millions of galaxies have produced hints at moderate statistical significance that dark energy may not be perfectly constant, and that its strength may have declined slightly over the last several billion years. The significance is not yet at the level that settles anything. The interpretation depends on how the data are combined with other measurements, and the history of this field contains a number of moderately significant hints that later evaporated. It is worth knowing about and not worth building on. What follows assumes a constant, which is what the weight of current evidence supports. Which brings us to the future, and the future has been worked out in considerable detail. The most thorough treatment is by two astrophysicists, Fred Adams and Gregory Laughlin, who published a technical paper in 1997 and then a book in 1999, extending the physics forward as far as it can honestly be taken. Their organizing device is a set of eras, each defined by what is producing energy. We are in the first, which they call the stelliferous era, the age of stars. It began a few 100 million years after the beginning, and it will end when the last star stops burning. That is a long time from now, but the era is already past its peak. The rate of star formation across the universe reached its maximum about 10 billion years ago and has been declining since. The universe now forms stars at roughly 1/30th of that peak rate. The gas is being used up, and it is not being replaced. The stars that will outlast everything are the smallest ones. A red dwarf with 1/10 of the Sun's mass burns its hydrogen so slowly and circulates its interior so thoroughly that it can use nearly all of it, that it can shine for something like 10 trillion years. The Sun will have been dead for 1,000 times its total lifetime before the last red dwarfs go out. Adams and Laughlin place the end of the stelliferous era at around 100 trillion years, which is 10 to the power of 14. At that point, the universe still contains a great deal of matter, but none of it is generating light. This is the degenerate era. What remains are white dwarfs cooling toward the temperature of space, neutron stars doing the same, brown dwarfs that never ignited, planets, and black holes. Occasional events still occur. Two brown dwarfs may collide and produce a star that burns for a while. A white dwarf may accumulate enough material to detonate, but these are isolated flashes in an otherwise dark cosmos, separated by immense stretches of time and by distances that keep growing. Whether the degenerate era ends depends on a question that is still open. Many attempts to unify the fundamental forces predict that the proton is not permanently stable and that it eventually decays into lighter particles. Experiments have searched hard for this. The Super Kamiokande detector in Japan is a tank holding 50,000 tons of ultrapure water a kilometre underground, surrounded by more than 11,000 light sensors, watching for the flash of a single proton coming apart among the enormous number in the tank. None has been seen. The current limit is that the proton's half-life exceeds 10 to the power of 34 years, and various theories place it between 10 to the power of 36 and 10 to the power of 39. If protons do decay, every white dwarf, every neutron star, every planet, and every remaining atom eventually dissolves. The dead stars glow faintly for a long stretch, heated from within by their own disintegration, radiating at a few billionths of a watt, and then they are gone. If protons do not decay, the matter persists, but the story ends the same way for a different reason and on a longer timescale. Either way, black holes are last. They evaporate through Hawking radiation, extraordinarily slowly, and the rate falls sharply with increasing mass. A black hole of 3 solar masses would take about 10 to the power of 66 years to evaporate completely. A supermassive one at the center of a large galaxy, with 10 billion times the Sun's mass, takes something like 10 to the power of 100 years. That figure is often given without comment, and it deserves one. The age of the universe so far, expressed in the same units, is 10 to the power of 10 years. The gap between the exponents is the entire story. When the last black hole releases its final burst of radiation, the universe contains no structure of any kind. Only photons, neutrinos, electrons, and positrons spread thinner and thinner through a space that continues to expand. The temperature approaches absolute zero without ever reaching it. Nothing can be built, because building requires a difference in temperature or density to draw energy from, and there are no differences left. This is the state sometimes called heat death and sometimes the big freeze, and it is not a catastrophe. It is the absence of any further events. There is one detail in this picture that unsettles physicists more than the emptiness does. In 1979, Freeman Dyson published a paper arguing that life could persist indefinitely in an expanding universe by slowing its metabolism to match the falling temperature, hibernating for longer and longer intervals, and thereby experiencing an infinite amount of subjective time on a finite budget of energy. It was a careful piece of work and, for a while, a genuinely consoling one. The acceleration destroys it. In a universe with a cosmological constant, there is an event horizon, and an event horizon means a finite total amount of energy will ever be accessible to any observer, and a finite amount of information can ever be processed. Lawrence Krauss and Glenn Starkman worked out the implications in 2000. Eternal thought is not possible in an accelerating universe. There is a last thought, somewhere in the far future. It happens at a specific time and there is nothing after it. And then there is the other possibility, which arises from the fact that a universe at maximum entropy is not perfectly static. It fluctuates. Over sufficiently long times, random fluctuations in the residual fields can produce ordered configurations by chance, and given infinite time, they produce every configuration that is physically possible, including, extremely rarely, a functioning brain, complete with a set of false memories of a life that never happened, existing for a moment in the void before dissolving. These are called Boltzmann brains, and the problem they create is not that they might exist. The problem is arithmetic. If the universe persists for an unbounded time in a fluctuating state, the number of such randomly assembled observers exceeds the number of ordinary observers who evolve through normal processes by an unimaginable factor. Any theory that predicts this outcome predicts that a typical observer is a fluctuation rather than a person, which means it predicts that your memories are false and your observations are unreliable, which means it undermines the evidence that was used to construct the theory. Cosmologists generally treat this as a sign that something in the framework is wrong, rather than as a conclusion to be accepted. Which framework, and what is wrong with it, is not agreed. So the standard picture arrives at a specific and rather bleak destination, reached by extrapolating measurements we trust across timescales for which we have no independent check whatsoever. There is an alternative reading of the same data. It is a minority position, published in a leading journal by a well-regarded theorist, and it holds that the expansion of the universe is not happening at all. Christoph Wetterich holds a chair in theoretical physics at the University of Heidelberg. His reputation rests on technical work in quantum field theory, particularly on methods for tracking how physical quantities change with the scale at which they are measured. He also has a specific claim on the subject of dark energy. In 1988, a decade before the acceleration was measured, he proposed that the vacuum energy might not be a fixed constant, but a dynamical field evolving over cosmic time. The same idea was advanced independently that year by Bharat Ratra and James Peebles. It later acquired the name quintessence, and it remains the leading alternative to a plain cosmological constant. In 2013, he posted a paper with a title that gives away nothing: A Universe Without Expansion. The proposal is this: the universe does not expand, space is not stretching. Instead, the masses of all fundamental particles increase steadily over cosmic time, and everything we interpret as evidence of expansion is a consequence of that increase. The mechanism runs through atomic physics. When an electron in an atom drops from one energy level to a lower one, it emits a photon whose energy is set by the difference between the levels. Those energy levels are proportional to the mass of the electron. A lighter electron produces lower energy transitions, which means longer wavelength light, which means redder light. Now look at a distant galaxy. The light left it billions of years ago. In Wetterich's picture, the particles in that galaxy at that time were lighter than the particles in our laboratory today. The light they emitted was therefore intrinsically redder than the equivalent light we produce now. When we compare the two, we find a shift toward the red, and we interpret it as evidence that space stretched during the journey. But the space did nothing. The reference standard changed. We are comparing ancient light against a modern ruler, and the ruler has grown. The cosmic microwave background follows the same logic. In the standard account, it was released hot and has cooled because expansion stretched its wavelengths. In Wetterich's version, the wavelengths are unchanged, and the apparent cooling reflects the growth of particle masses relative to the fixed photon energies. The universe is not getting colder, we are getting heavier. The immediate objection is obvious, and Wetterich addresses it directly. Everything we use to measure mass is itself made of particles whose masses are increasing. Every ruler, every scale, every atomic clock, every standard of comparison grows in step. There is no internal experiment that could detect the change, because the change is universal. It is not observable from the inside, and it does not need to be, because it produces exactly the observations we already have. The model requires the gravitational constant to vary in a compensating way, and Wetterich shows that when it does, the framework reproduces the successes of standard cosmology. The spectrum of the microwave background, the growth of large-scale structure, and the abundances of hydrogen, helium, and lithium produced in the first minutes. It does this without a singularity. In this picture, the universe has no first moment. It extends infinitely into the past, in a nearly static state, with the particle masses slowly rising from an extremely low value. The hot, dense early universe is hot and dense not because it was compressed, but because the particles were light and the energy scale of their interactions was correspondingly low. The press coverage was predictable and largely wrong. Headlines announced that the Big Bang had been disproved. Wetterich spent the following weeks giving interviews in which he explained that he had done nothing of the kind. Here is what he had actually done, and it is more interesting than the headlines. The two pictures are related by a mathematical transformation. General relativity has a property that is easy to state and slippery to absorb. It contains no absolute standard of length. Nothing in the equations specifies how long a meter is. Every measurement in physics is ultimately a comparison of one quantity against another, and what we actually observe is a ratio. When we say a wavelength has stretched, what we have measured is that the wavelength is now larger relative to the size of an atom in our laboratory. That single observed ratio can be described in two ways. Either the wavelength grew while the atom stayed fixed, or the atom shrank while the wavelength stayed fixed. Both descriptions encode the same physical content. The choice between them is a choice of which quantity to hold constant, which is to say a choice of units. Standard cosmology holds particle masses fixed and lets space expand. Wetterich holds space fixed and lets particle masses grow. The two are connected by a rescaling of the metric, and every prediction that can be checked comes out identical because they are descriptions of the same thing in different coordinates. This is not a refutation of the Big Bang. It is a demonstration that the singularity at the beginning is not necessarily a physical event. In the standard frame, distances between particles shrink to zero at a finite time in the past, and the equations produce infinities. In Wetterich's frame, that same moment corresponds to particle masses going to zero, which is a smooth limit that the mathematics handles without breaking. The infinity was an artifact of the coordinates. Change the coordinates, and it goes away. Whether that means anything is a real and unresolved question. Some singularities in general relativity are genuine features of the geometry and cannot be removed by any change of description. Others are artifacts of a badly chosen coordinate system, and physicists have been fooled before. The apparent singularity at the event horizon of a black hole was regarded as a physical barrier for decades until it was shown to be a coordinate artifact, removable by a suitable change of variables. The singularity at the center is not removable in the same way. Wetterich's model does not enjoy wide acceptance, and the reasons are worth stating. It is not simpler than the standard picture. It requires a carefully arranged evolution of the fundamental constants to reproduce what expansion and dark energy achieve with fewer moving parts. It has generated no distinctive prediction that would let anyone test it against the standard model, and a framework that is mathematically equivalent to another framework offers, by definition, no observational reason to prefer it. Wetterich himself has been careful in interviews, describing the Big Bang as a very successful working hypothesis, and his own work as an exploration of what else is consistent with the evidence. What the exercise demonstrates is a property of scientific knowledge that is rarely made this explicit. The Big Bang is not an observation. Nobody has seen it. What has been observed is that distant galaxies are redshifted in proportion to their distance, that the sky glows faintly in the microwave band, and that the universe contains particular proportions of the light elements. The Big Bang is an inference drawn from those observations within a particular theoretical framework, and it is an extremely good inference. But a different framework can accommodate the same observations, and when one does, it shows that the link between what we see and what we conclude is looser than a textbook makes it appear. This has direct consequences for everything covered tonight. Each of the pictures we have looked at rests on an inferential chain reaching well past what has been measured. The infinite universe rests on flatness plus an assumption of uniformity beyond the horizon. The bubble multiverse rests on inflation plus a particular reading of the string landscape. Many worlds rests on taking the Schrödinger equation as complete. The dark flow rests on a contested extraction of a faint signal. None of these is unreasonable. Every one of them is a step past the data. Wetterich's model does not change what the future looks like, incidentally. In his frame, the masses continue to grow, the effective temperature of the background continues to fall, and the universe arrives at the same cold, dilute, featureless state as the standard model predicts. The ending is unchanged. Only the beginning is different, and the difference is that there is not one. Which leaves one question standing, and it is the question underneath all of the others. Every model in this script takes a set of physical laws as given, and works out what follows. Nobody has explained where the laws come from. The mass of the electron is measured, not derived. The strength of gravity is measured, not derived. The number of spatial dimensions is observed, not explained. If eternal inflation is right, these are local accidents. But the deeper laws that govern which accidents are possible, the mathematical structure within which the landscape of vacua exists at all, is still handed to us without justification. There is one more hypothesis, and it is the most extreme thing anyone has proposed. It says that the question is malformed, because there is no selection to explain. In 1960, the physicist Eugene Wigner published an essay with a title that has outlasted almost everything else he wrote. He called it The Unreasonable Effectiveness of Mathematics in the Natural Sciences, and the argument in it is not complicated. It is simply that something is going on which nobody has explained. Mathematicians frequently develop structures for reasons internal to mathematics, pursuing questions of consistency or elegance with no reference to the physical world. And then, sometimes long afterwards, those structures turn out to describe nature with an accuracy far exceeding anything the original work could have anticipated. The examples are not rare. Complex numbers were introduced in the 16th century as a bookkeeping device for solving cubic equations, involving the square root of a negative quantity, which was regarded as obviously meaningless and merely useful. They were called imaginary as an insult that stuck. 400 years later, they turned out to be structurally required by quantum mechanics, not as a convenience but as an unavoidable feature of the way physical states combine. Bernhard Riemann developed the mathematics of curved spaces in 1854, generalizing geometry to any number of dimensions and any pattern of curvature, motivated entirely by the question of what geometry could be if you dropped Euclid's assumptions. 60 years later, Einstein needed exactly that machinery to write down general relativity, and found it waiting, complete. Group theory was developed in the early 19th century by Évariste Galois to determine which polynomial equations can be solved by radicals. Galois died in a duel at 20, having written out much of it the night before. A century later, group theory turned out to be the organizing principle of particle physics, with the fundamental forces classified by their symmetry groups, and the existence of particles predicted from the structure of the mathematics. The most direct case is Paul Dirac in 1928, trying to write an equation for the electron that respected both quantum mechanics and special relativity. The equation he produced had solutions with negative energy, which appeared to be nonsense. Rather than discard them, Dirac worked out what they would correspond to physically and concluded that there must exist a particle identical to the electron, but with opposite charge. Nobody had seen such a thing. 3. 4 years later, Carl Anderson found the positron in cosmic ray tracks. The particle was discovered because the mathematics had a solution in it, and Dirac took the solution seriously. Wigner's essay does not resolve this. He calls it a wonderful gift which we neither understand nor deserve, and stops there. It is a very unusual thing for a physicist to publish, a careful description of a problem, followed by an admission that he has no idea. Max Tegmark's answer is to remove the mystery by removing the distinction that creates it. His argument starts from a position most working scientists hold, that there is an external physical reality which exists independently of human beings. If that is true, Tegmark argues, then a complete description of it must be expressible without any reference to human concepts, because those concepts are features of us rather than of it. Words like particle, energy, and even space carry human associations. Strip out everything that depends on a human perspective, and what remains is a set of abstract entities defined solely by their relations to one another. That is precisely the definition of a mathematical structure. So a complete description of reality is a mathematical structure. Tegmark's step is then to argue that the description is not merely a description. If reality is perfectly captured by a mathematical structure, with nothing left over, then there is no remaining content to the claim that reality is something additional, which the structure describes. The structure and the reality are the same object, and if our universe is a mathematical structure, there is no principled way to grant it existence while denying existence to the others. Nothing distinguishes it. There is no mechanism that selects one structure and makes it physical while leaving the rest abstract, because a selection mechanism would have to operate from outside all structures, and there is no outside, so all mathematical structures that are internally consistent exist in exactly the sense that ours does. This is the fourth level, and it is the last one, because there is nothing further to generalize. The ensemble includes structures with different numbers of dimensions, different logical foundations, different notions of time, or none at all. Most contain nothing resembling an observer. A structure has to be complex enough to support persistent self-referencing patterns before there is anyone inside it to notice anything. And the overwhelming majority are too simple, too rigid, or too chaotic. In the small subset where observers are possible, those observers find themselves in a structure that permits their existence, and wonder why the laws are so finely suited to them. The answer, in this framework, has the same form as the answer to why we find ourselves on a planet with liquid water. Tegmark has said that he finds this idea elegant rather than disturbing, and he means something specific. If it is right, the question of why there is something rather than nothing dissolves. Mathematical structures do not require causes. The number 7 does not need an explanation for its existence, and neither does the set of integers, and neither, on this view, does the universe. Nothing had to happen. Existence is not an event. The criticisms are substantial, and they are not merely reflexive. The most common is that Tegmark equivocates between two senses of the word exist. A mathematical object exists in the sense that its properties follow from its definitions. A rock exists in the sense that it has mass, occupies a location, and can be dropped on your foot. These are different relations, and asserting that they are the same relation is a claim requiring argument rather than a conclusion to be reached by noticing that the same verb is used for both. The second objection is technical, and, in the view of many, more damaging. The ensemble is supposed to consist of all logically consistent mathematical structures, but consistency cannot always be established. In 1931, Kurt Gödel proved that any formal system rich enough to describe basic arithmetic cannot prove its own consistency using only its own methods. There is no general procedure for sorting structures into the consistent and the inconsistent. If the criterion defining the ensemble cannot be applied, it is not clear that the ensemble is well defined, and an ill-defined collection of everything is not obviously better than an unexplained collection of one. Tegmark has responded by proposing a restriction to structures that are computable, which sidesteps some of the difficulty at the cost of excluding a great deal of mathematics, including most of the continuous mathematics currently used in physics. The third objection concerns probability. If all structures exist, we ought to be able to say something about which sort of structure a typical observer inhabits, and thereby extract a prediction. Doing so requires a way of weighting an infinite collection, and there is no natural way to do it. Different weightings give different answers, and nothing selects between them. This is called the measure problem, and it afflicts the second level as much as the fourth. It is the single largest technical obstacle to making any multiverse framework predictive rather than merely permissive. And the last objection is the plainest. There is no observation that could distinguish a universe in which all mathematical structures exist from one in which only ours does. No experiment discriminates. Tegmark accepts this for the fourth level, while arguing that the first three levels make contact with testable physics at various points, which is true, and which is also a considerable retreat from a unified framework. Where that leaves it is roughly here, an idea that is internally coherent, that follows from premises many physicists accept, and that cannot be tested, argued over by people who agree on all the observable facts. There is one more thing to place before the end, and it comes from the man who supervised Everett's thesis. John Archibald Wheeler spent the last stretch of his career on the question of what the universe is made of at the deepest level, and in 1989 he compressed his answer into 3 words: it from bit. His proposal was that physical things derive their existence from binary answers to yes or no questions, from the resolution of quantum alternatives, from information rather than substance. Every particle, every field, every space-time interval takes its meaning from the answers to questions that could be asked about it, and beneath that, there is nothing further. Wheeler did not claim to have demonstrated this. He described it as an idea he could not prove and could not abandon. He was aware that he had spent his career supervising students who took his suggestions further than he did, and he seemed to regard that as the correct outcome. If something like it is right, then the thing that constitutes you is not the specific atoms currently in your body. Those are replaced continuously and will be entirely different within a few years. What persists is a pattern, a particular arrangement of relationships running on whatever matter happens to be available. A pattern is the kind of thing that can be instantiated more than once, which returns us to the room. The number from the beginning of tonight was 10 to the power of 10 to the power of 115 meters, and now it can be stated precisely. That is the distance to the nearest region the size of our entire observable universe that is identical to ours, atom for atom, across all 46.5 billion light-years of it. Every galaxy in the same place, every star with the same mass. The same history, run through from the same beginning to the same present moment. The nearest copy of you alone is closer, because you are a much smaller thing to specify. That distance is roughly 10 to the power of 10 to the power of 29 meters. The exponent falls from 115 to 29, a reduction so severe that in ordinary arithmetic the two numbers would have nothing to do with each other, and which makes no practical difference at all. Both lie beyond every horizon. Both are unreachable in the same permanent way. Neither number is a metaphor. Each follows from a specific chain. That space is flat, which has been measured, that it continues beyond the horizon with the same properties, which is an assumption. 2. That the information content of a finite volume is bounded, which comes from the thermodynamics of black holes, and that a finite set sampled infinitely often repeats, which is not physics at all but counting. If the chain holds, then somewhere at that distance there is a room. The dimensions are the same as the dimensions of the room you are in. The air is the same temperature. There is a person in it whose memories are your memories, arranged in the same order, containing the same names. That person heard this sentence at the same moment you did, and had whatever response you had to it, and is now doing whatever you are about to do. You will never receive any evidence of this, neither will they. The space between is expanding, and no signal sent in either direction at any point in the remaining history of the universe would arrive. While you have been lying there, particles of dark matter have been passing through you, billions of them every second, moving through the walls, through the bed, through your body, interacting with none of it. We can map where dark matter is by watching how it bends the light of distant galaxies. We can weigh it. We have known for 50 years that it makes up the great majority of the matter in the universe. We have no idea what it is. Detectors have been built in mines and under mountains and in Antarctic ice, shielded and cooled and watched for decades, and none of them has recorded it arriving. The cosmic microwave background is also passing through the room. It has been travelling for 13.8 billion years, since 380,000 years after the beginning, and it arrives now at 2.725 Kelvin. It came from every direction, from the surface where the fog lifted, and a very small fraction of the static on an untuned analog television was always this. It is the oldest thing anyone will ever detect, and it is passing through the room at the ordinary speed of light, and it is not stopping. It is getting colder. It will continue to get colder for as long as the expansion continues, which on current evidence is without limit. The galaxies are still there, for now. Beyond the local group they are receding, and one by one, over the next 100 billion years, they will cross the boundary past which nothing they emit can ever reach us again. The clusters are still drifting toward a point between Centaurus and Vela, or they are not, and the argument about which continues in journals. Further out, past the boundary of what light can show, the space continues. The evidence does not tell us how far. The simplest reading of it says there is no end. Somewhere out there, at a distance with 115 digits in its exponent, the room is repeated. Some of them are already asleep. Good night.